In this video, we'll talk about equipotential surfaces. An equipotential surface is defined as a surface consisting of a continuous distribution of points having the same electrical potential. Or put another way, they're at the same voltage. So I've drawn a surface that I'm saying is equipotential. Then if you're talking about measuring the voltage from A to B, so let's say that we hook a voltmeter up between A and B, so this is the plus side of the voltmeter and the minus side of the voltmeter, then what that's going to measure is 0 volts. Point A and point B have exactly the same electrical potential. Likewise, point C and point D would have the same electrical potential, and point D to point A would be the same. In fact, any 2 points that I put my voltmeter between on this surface, if it's equipotential, would give me a reading of a potential difference of 0 volts. Now, you could have some other place over here, call it point Z, and you could have defined that to be the 0 potential reference point. When we do that, we often say that that point is ground, and this symbol that looks like a Christmas tree with smaller little dashed line, that is ground. That's the symbol for your reference point. Point D might be 10 volts plus with respect to that ground. That is, if we ran a voltmeter between this point minus plus. But if we ran a voltmeter between there, say point C, and point E, we would again get 10 volts. If we measured the difference between D and C, 10 minus 10, we would get 0. Remember, voltage at a point never has meaning without a reference. If we're using this as our reference, we would say every point along this surface is 10 volts, or that's an equipotential surface of 10 volts. So with a voltmeter, we can actually map out places in space of equipotential lines. And there are, in fact, some labs in schools that do this. Now, if it has equipotential, and we multiply by Q, then we're talking about potential energy. So from the definition, an equipotential surface is also a constant potential energy surface. That means that the potential energy of an object as it moves along this surface will not change. So there's point A, and there's point B, and there's point C. So if you were to put a charge, say right here, there is no reason that that charge would want to pick up speed and move along this. In fact, it can. Remember, we're talking about the electric field, which is a conservative. So that's 0, and this is equal to delta E, which is delta K plus delta U. So delta K would be minus delta U. But we just said it's equipotential, which means this is minus Q delta V, and that V is 0. So this particle will not pick up speed and move. This is much like being on the floor. Say you're on the 2nd floor of a building and you're walking around. You don't pick up speed as long as you're walking on the level floor, because that's an equigravitational potential surface. If you step out the window, then you pick up speed and you lose potential energy because you're moving between different heights, different potential surfaces. So as long as the particle stays on this surface, it would not pick up any speed. It would keep whatever speed it has, and its kinetic energy would be constant. Now, what if it gets off that surface? Well, this is an important point. So let's go back again and look at our surface. If along this surface, say between these points, A, B, and C, then what that tells you is that if you go along this surface, let me change color pins here, and you have some delta R, work is QE dot delta R. But I just said that that's also minus Q delta V. And delta V is 0. So there's no work along that path. Well, if you've got a displacement and you have an electric field, the only way that this can be equal to 0 is because E delta R cosine theta is 0. E is not 0. Delta R is not 0. So cosine of theta must be 0. That means theta has to be 90 degrees. This says that the electric field is perpendicular to the equipotential surface at every point on the surface. So if I'm drawing electric field lines, the electric field must either be pointing that away or pointing that away. Likewise here, the electric field must be perpendicular. 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 At each point, the electric field is perpendicular. Now, whether it's pointing down or up, that we don't know. We'll have to talk about in the next thing. And that has to do with the direction that the particle will experience a force to gain or lose energy. All right? But it is definitely perpendicular. So if you know the field lines, if you draw the field lines, for instance, for a charge distribution, you can then draw the direction of the equipotential surfaces by simply drawing them at right angles to your field lines. The electric field points in the direction of decreasing electrical potential. What does this mean? This means that if you map some different equipotential surfaces, let's say this is at 40 volts, and you had another line here at 30 volts, and you had another line of equipotential surface of 20 volts. The electric field is perpendicular to the surface and points toward the lower voltage surface. So from 40 to 30. It would have to go in here, strike this also at right angle, and head to the 20. So our electric field lines here have to be like this. Over here, the electric field line must be perpendicular to that surface, perpendicular to that surface. So it's got to actually turn like so. Always falling downhill. Think of higher voltage as being higher on the hill. Down voltage like rolling downhill. So it's as if you lower gravitational potential energy. That is, when you let something go, it rolls downhill to a lower height. In the same way, that's the way the force pulls it with gravity. The electric field points in the direction of decreasing electrical potential. Now, its charge is going to go in decreasing potential energy. Whether or not the 30 is lower in energy than the 40 depends on the charge. If the charge is positive, then the 30 is lower in potential energy than would be the 40. But if it's a negative charge, a minus 30 times Q is actually larger than minus 40 Q. So negative charges appear to go up in the potential rather than down. They go in the opposite direction. Positive charges move. Now, as an example of that, I'm going to very quickly sketch the potential lines and the equipotential surfaces for a set of charge distributions. And you may remember me doing this earlier. We take one line straight from the 3Q to the minus Q, and then we have to take two lines that go out to infinity to keep the line distribution. We have another line goes from the plus Q to the minus Q on both top and bottom, and that means we need two more lines going out like this. We have a line coming in, something like this, not the world's best drawing. And we have one more field line going like this, and a field line going like that. A field line going out like this, and a field line going out like that. So there's my electric field lines. The equipotential surfaces are perpendicular to the line. So this should be perpendicular here, perpendicular there, has to slightly turn, and has to turn like this, going down like this, straight, straight, starting to turn. Right around here we'd have a line, again trying as best I can to make them perpendicular at each point. Around something like that. Over here, whoops, trying to make them perpendicular to my lines as best I can. Something like that. Here. Something like that. So you can make a rough estimate. The key thing is to try to find a way as best you can by hand to make these at 90 degrees. If you put a charge here, moving along here does not pick up energy. Moving in this direction picks up speed because it converts potential energy into kinetic energy as the positive charge moves in this direction. All right. I'll see you on another video.